Today, we are going to be talking about balanced three-phase circuit analysis. This will actually be what we're going to talk about for several days. So let's consider a YY three-phase circuit. In which we have a Y connected source having voltages VAN, VBN, and VCN. And then over here, we're going to have a Y connected load. Having impedances ZYA, ZYB, ZYC, like so. And connecting our source to our load will be a network of transmission lines. Having impedances of ZWA, ZWB, ZWC, and ZN. Okay. So this circuit will be balanced under the following criteria. The magnitude of our phase voltages at the source need to be equal. So the magnitude of VAN, VBN, and VCN need to be the same number, which I will call as a shorthand notation VP. The phase separation between the phase voltages at the source is 120 degrees. So that means angle theta BN has to equal angle theta AN minus 120 degrees. And angle theta CN will be equal to the angle theta AN minus 240 degrees. Technically, this is true only for a positive phase sequence system, right? If I change the sign to plus 120 and plus 240, this would still represent a balanced three-phase system. It would just be one in which there is a negative phase sequence, okay? But since we're going to work pretty much strictly with positive phase sequences in this class, I'm going to leave this as said. So on the source side, then, we have a balanced three-phase source when the magnitude of our phase voltages are equal, and we see exactly 120 degrees of separation between each phase. All right. For our middle section, the transmission lines, we also need to have them as a balanced system in order for the whole system to be balanced. So the impedances ZWA, ZWB, and ZWC need to be identical. Which I might use as a shorthand notation, the representation ZW, okay? Now I want you to notice the impedance of our neutral conductor here is not mentioned. We'll find out why, but for a balanced three-phase system only, the A phase line, B phase line, and C phase line need to have identical impedances in order for our system to be considered balanced. So let's talk about what that would represent in a real system. Effectively, the A, B, and C phase transmission lines need to be made of the same type of wire and have the same length. If those two conditions are not met, it's likely an unbalanced system. Okay.
I think there's some tolerance. They'll make close enough to balance system if they're off by.
Right. So yeah, we're not going to get a scanning electron microscope or anything like that and make sure that the lengths of these things are absolute. But as long as you're within a couple of inches, it should not be that big of an issue. Finally, on the load side, for us to have balance, we must have the quantities ZYA, ZYB, and ZYC equal, which I will represent as just a single Z1. So under these four constraints, we have a balanced YY system. Let's talk about what that means and what that entails by looking at our line currents. Okay. So I am going to define four line currents. IAA, IBB, ICC, and this guy down here, INN, as a line current, since it passes through a transmission line as well. Okay. So what I'm going to do is I am going to just set one node in this system to be ground or be a reference to make my life easier. And I am going to choose the source side neutral as my reference. Okay. Now, in reality, a three-phase system like this is not connected to ground at all. But I'm just going to choose this node to be my reference to be able to refer things back to. Okay. So if I apply Kirchhoff's current law at my load side neutral node, what I get is IAA plus IBB plus ICC plus INN is equal to 0. And I'm going to use Ohm's law now to express these four currents in terms of some impedances. So let's talk about that just real quick, okay? So IAA is the current that flows through impedance ZWA and also through impedance ZYA. The total voltage drop would be this voltage VAN, which is measured with respect to ground, minus this voltage, which will be V capital N lowercase n. Okay. So from that, I can rewrite this as VAN minus V capital N lowercase n divided by ZWA plus ZYA plus VBN minus V capital N lowercase n divided by ZWB plus ZYB plus VCN minus V capital N lowercase n divided by ZWC plus ZYC minus V capital N lowercase n divided by Zn is equal to 0. Let me just explain where the minus sign is coming from. So with a plus sign, this would look like V lowercase n uppercase n divided by Zn because the current is flowing to the right. Since I am trying to find everything in terms of Z capital N lowercase n, effectively I want the current flowing in the opposite direction, which is where that negative sign comes from. Okay, so the negative sign was not a mistake. For a balanced network, this expression reduces to V capital N lowercase n divided by Zn is equal to VAN minus V capital N lowercase n divided by ZW plus ZY plus VBN minus V capital N lowercase n over that same ZW plus ZY plus VCN minus V capital N lowercase n divided by ZW plus ZY, which I can slightly rearrange as V capital N lowercase n multiplied by 1 over Zn plus 3 over Zw plus Zy is equal to VAN plus VBN plus VCN divided by ZW plus ZY. So when our source is balanced, what does VAN plus VBN plus VCN equal? I made you guys do this the other day. It was 0, right? So if this term is 0, which will be true if the magnitude of the voltage drops are equal and they are all separated by exactly 120 degrees, that implies that VNN has to be 0 as well, right? Because if the right-hand side of my equation is 0, unless I have no impedances anywhere, VNN needs to be 0 for this to be true. Is everybody okay with that? All right, so from this result, we can see a couple of things. INN, the current flowing through my neutral conductor, is negative VNN over Zn. Sorry, that should be uppercase, which is 0 amps. Which means in a balanced three-phase system, there is no current flowing through my neutral conductor, regardless of what its impedance is. So if it's a short circuit, there's no current. If it's an open circuit, there's no current, and any impedance in between, there is also no current, which is why the neutral conductor is optional. The purpose of the neutral conductor is to carry phase imbalance, okay? So the reason why neutral conductors exist in real three-phase systems is because of any potential imbalances that may occur. If you were to look in the National Electronics Code standard, the size constraint for the neutral conductor is different than the size constraint of your phase conductors because it's not expected to actually be in use very often. Okay, so it's got its entirely own section in the code book for how to properly size that guy. So if IAN is equal to 0, let's talk about our other line currents here real quick. So IAA is going to be VAN minus VNN over ZWA plus ZYA, which reduces to simply VAN divided by ZW plus ZY for our balanced system. IBB is VBN minus VNN over ZWB plus ZYB, or VBN angle ZW plus ZY, or VAN over ZW plus ZY multiplied by a scaling factor of 1 angle negative 120 degrees. And finally, ICC is going to look like VCN minus VNN ZWC plus ZYC, or VCN over ZW plus ZY, which is the same as VAN over ZW plus ZY times 1 angle negative 240 degrees. Okay. So let's talk about these results here. Okay. I'm doing these identities effectively because I know for my voltages, they have the same magnitude and they're exactly shifted by 120 degrees, right? So B lags A by 120, C lags B by an additional 120, or lags A by 240. So if I have a balanced three-phase system, my neutral current is 0, and my line currents represent a balanced system as well, right? Because they all have the exact same magnitude and they all have a phase separation of exactly 120 degrees. So if that's how my line currents behave, what about my phase currents in my load? Well, they're literally the exact same thing. So all of the phase currents in my load should have the same magnitude and be separated by 120 degrees. The phase currents in my source will have the exact same magnitude and have the phases separated by 120 degrees. Since the currents flowing through my load impedances all have the same magnitude and are separated by 120 degrees, that means the voltage drops across my impedances also have the same magnitude and are separated by 120 degrees. Phase voltages and line voltages will behave that way, okay? So in a balanced three-phase system, everything, like every individual quantity, has the same magnitude and their phase angles are separated by 120 degrees, which means we don't actually have to analyze the three-phase system as a whole to get any results. We can analyze it as a single-phase equivalent circuit and then simply shift everything by 120 degrees to understand what's going on in the B phase and what's going on in the C phase if we know what's going on in the A phase. So let's talk about that single-phase equivalent circuit representation. So, since we know that VNN, the voltage drop across our neutral conductor, is 0. And we know that INN, the current flowing through our neutral conductor, is 0. We can treat our neutral conductor as a short circuit regardless of what its actual impedance is, because in a balanced three-phase system, it's always going to look like a short circuit, okay? Even if it's an open circuit, it still behaves like it's a short circuit. Absolutely. Because the voltage drop over it is 0, and the current flowing through it is 0.
I thought you were saying the current could flow through it.
So the current flowing through the circuit will always be 0. So when I say an open circuit, I'm talking from terms of its impedance, an infinitely large impedance, right? No current will ever flow through it in a balanced system, okay? But no voltage drop occurs over it as well. So it is behaving as if it were a short circuit and an open circuit simultaneously, actually, okay? I know it's weird, but that allows us to create this much simplified model, okay? So instead of looking at a three-phase model, we can look at 3 single-phase models. So our A-phase model would look something like this. Our B-phase model, it should be VAN. This will be VBN. This is ZW, this is ZY. And finally over here, we'll have our C-phase model. Like so. And I'm going to represent my line currents. IAA, IBB, and ICC as such. Okay. So this is how we make a YY system look like 3 single-phase systems, which would easily allow us to determine our line currents, our phase currents at the load, our phase currents at the source, our phase voltages at the load, not our line voltages at the load or source, for any of our 3 phases, okay? I feel very strongly that with you guys' electrical engineering background, you can analyze this single loop circuit to death at this point, okay? So I'm not going to trouble you with a numerical example on this particular thing right now, because again, I feel very strongly that you guys know how to analyze a circuit with 3 elements in it, and they're all connected in series, okay? This single phase equivalent circuit is only valid for a YY system. So because I have to cut class short today, what we are going to address on Wednesday is transformations to make any any delta connected source look like a Y connected source, and any delta connected load look like a Y connected load, so that we can apply this trivial single phase equivalent circuit model to any three-phase circuit that we encounter. All right, so that's enough out of me for today.